Okay, welcome back. In this video, we are going to continue our discussion on analyzing trusses. Last time we did method of joints. This time we're going to do method of sections. The difference here really is with method of joints, you're looking for the force in every single member, or typically a member really close to one of the reactions. You're going to use the method of sections when you want to actually just find the force in a particular set of members, maybe 1, 2, or even 3 members of a truss. So the process actually starts off the same as if we were doing method of joints, where we're going to start off by finding the external reactions, but as a second step, instead of choosing a joint, we are going to choose a section based on what you want, meaning the section is going to go right through the members that are unknown that you're looking for. And the third step is we are going to solve for those members using your basic static equation. Sum of the forces x equals 0, sum of the forces y equals 0. Now this one we are going to use some of the moments about a point is equal to 0, but it's not overly difficult. So let's go ahead and take a look at an example. And here's my example, and what I have is a truss. I can see I have these two 6,000 pound forces, one applied at C, one applied at E, and it is symmetric, but the loading is not symmetric, so I cannot take 12,000 and put it to each side. So the first step, well, let's talk about what we're trying to find here first. We're trying to find the force in members CE, DE, and DF. So what is that? CE, this member, DE, and EF. No, DF. So I can. So the method of joints would work. You'd have to do joint A, and then you'd have to go up and probably do joint B, and then joint C, and then joint D. But it'd be a lot more work. So let's start with finding our external reactions for this structure. I know that I have a pinned connection at K, so I'd have some kind of K in the Y direction, some kind of K in the X direction, and at A, I'd have some kind of A in the Y direction. So, I mean, to begin with, we could just say sum of the forces in X equals 0, so that Kx is equal to 0, knock that out of the way. And then let's do some of the moments about point A is equal to 0. And I'll go kind of quickly because this should be reviewed by this point. You never know though. KY, if I add up all those 12.5s, I end up with 62.5 feet for my distance, minus this 6,000 pound load times 25 feet, minus the other 6,000 pound load times its distance away, which is half that, 12.5 feet. Set that equal to 0, and I get a reaction at K that's equal to 3,600 pounds. Zoom over so you can see my work and the picture at the same time. And I can also do sum of the forces in the Y direction equals 0 to solve for this AY value plus this 3,600 minus these two 6,000 pound loads. I'm just going to combine them into one 12,000. And I end up with a total reaction of 8,400 pounds. So once I have those reactions, I can just draw them in, I suppose, if I really wanted to. AY was 8,400 and KY is 3,600. Totally optional on that bit. So step 2 in this process, we said we want to choose a section based on what we want. So what we want to know is the force in DF, DE, and CE. I have labeled there. Now, when you're going to do your section, you're going to put a line right through whatever you want to know. So I want to know DF, I want to know DE, and I want to know CE. So I can actually draw one continuous line. It's like breaking the truss right through those 3 pieces. Once I have that drawn, I can look at either the left or the right-hand side. I generally look at the smaller one because I figure there's usually going to be less loads and things. So let's look at the left-hand side and draw a free body diagram of what's going on here. So there's a free body diagram. All of that, I suppose, was step number 2, drawing this section through here and through what I want. And what I tend to do is I do draw these little nubs where I'm cut right through the section to remind me which kind of direction it's going. And the other thing that I do is I draw all of my members as if they are in tension, meaning I'm drawing the arrows away from the member. Just same thing we talked about with method of joints. If it points towards the member, be in compression. If it points away, it's in tension. So I'm assuming everything's in tension, which probably isn't right, but I'm consistent, so if I get a negative sign, I know it's in compression. So the third step is let's solve for my unknowns. I have 3 unknowns. I have 3 equations of statics. I can solve this. Now typically what you want to do is you want to start with sum of the moments about some point that would make 2 of your unknowns go away. So you're looking for a point where it'll intersect. If I extend 2 vectors along their directions, they'll make 2 go away. Now there's 2 possible ones here. One is right here at D, because if I did the sum of the moments about point D, then DF wouldn't have a lever arm, so it wouldn't be involved. DE wouldn't have a lever arm, so it's not involved, and I could solve for CE directly. Now the other option would be I can extend these on down and they both intersect at, what point is that? That's point E. So I could also do some of the moments about point E either way. If I did about point E, of course, it would have DE and CE not involved, and I'd only solve for DF. You want to think about this, even though it's not on the structure. You want to think of that possibility when, depending on what you're looking for. So there might be a time when you only want DF, or you only want the top chord or something. In that case, you wouldn't go through the hassle of doing all 3 equations if you don't need to. But I'm going to do some of the moments about D is equal to 0. We're sticking with our counterclockwise as positive notation. And so I have this negative 8,400, meaning it's creating a clockwise moment, and I have to find out my distance away. So I'm looking at this 8,400, and I see it's 6.5 plus 12.5 is its distance away from this point D, which is 18.75. And then I have that 6,000 pound force going the counterclockwise or positive direction, and its distance away is this 6.25 away from joint D. Hopefully you can see where these are coming from, because this is pulling down. I know it's symmetric, so it's straight up, so it's like half that distance of 6.25. And then last but not least, I have my unknown here, my FCE, and its lever arm, since I can see it would be this vertical distance. I don't know if I want to draw over this thing, but it's this vertical distance here, which is 15 feet, is equal to 0, and that gives me a force in member CE that's equal to 8,000 pounds. And I got a positive number, and because I got a positive number, that means that it is in tension. After I do that, I can, I could do some of the moments about E if I wanted to find F, DF. I can also go into my sum of the forces in the X or Y direction. I'm going to go into the Y direction first, and if I look at the Y, I have 8,400 up minus this 6,000 down, and then this FDE has a component that's down, so I only want the vertical component. So like last time, I have to come up here and say, what are my lengths and my directions and things, and what I would find out is that if I found the length of one of these members, I find out the length is equal to 16.25 feet, and that of course is just square root of 12.5 squared plus 15 squared. So if I wanted the vertical component of that, it would be the vertical distance of 15 divided by the length of it, 16.25, times the force, DE, and I say that's equal to 0. I can solve for FDE. So FDE, after I punch in my calculator, I get something like 2,600 pounds. I also got a positive number, which means it's in tension. So for my last member, now I can move into sum of the forces in the X direction equals 0. Oh, no, 8,400, 8,000 pounds, because I found that I found that CE to be 8,000 in the positive direction. Plus I have this 2,600, and its X component Now I'm saying, well, how far does it go in this? This is the same thing as it's splitting it in half. So I have that half of that x distance of 6.25 over the hypotenuse of 16.25 plus my last unknown of f df is equal to 0. And from that I can get f df that's equal to negative 9,000 pounds, or since I got a negative, I know that I guessed my direction wrong. It's actually in compression. So I would rewrite this as 9,000 pounds compression. It wouldn't really make sense to leave it as negative unless whoever is reading your work understands that negative sign just means compression. But I hope you found that helpful, and I look forward to talking to you soon. Thanks.